Hi, I'm Holly, and I'm going to look at Huffman Encoding. So before we do that, what we need to be looking at is the idea of compression. And the whole point of Huffman Encoding is to allow files to be compressed, whether they are JPEGs, whether they are text files. We're going to look specifically at text files, but before I do that, let's have a little look at how the types of compression work. First of all, we're going to look at lossless compression. Lossless compression is this idea that you don't take away data that isn't there. It's taking away data that we as humans don't actually need. Okay, so if we were going to look at a text file, what we would do is, first of all, we need to understand what a character set is. Now, in the GCSE, the first thing that we look at is if we have a character set, each of the letters or symbols on the keyboard, every single one of them is going to need to have a number assigned to it, and then that automatically then leads on to a conversation about binary. Now, each character within our ASCII character set has 8 bits, which equates to 1 byte. And that each one of those characters requires a little bit of memory. And if we took the whole of our file, we would need to have in there huge volumes of data. So what we can do is, rather than assigning something for every single character that could possibly be recorded, what we could do is potentially take away our duplicated data. So looking initially at 2 random words, we've got pineapple with a space and then banana. We've then got 16 different characters here. We could assign every single character a value, or what we could do is we could take just the characters that we've used within our two words. Here, we've then got 8 different characters. If we then took this concept of assigning the number 8 to binary, and we show them as a bit pattern, what we can do is we can assign different bit patterns to each of those characters. Here we've got 1, so that is the smallest number of bits, so it's just a 1 for the P, 1 0 for the I, 1 1 for the N, and carrying all the way up to our 4 1s for the B, being the smallest amounts that we could show our bit patterns in. So no leading zeros. Now in our message, what we've ended up with there is an ambiguous number. So once we've received it, we then need to know how to decode our message. So with our ambiguous number, that could be PN, or is it NP? And if you remember, 111 was also space. So technically, this could have been any of them. And when we're decoding, we don't actually know how to do that. So what we need is a way of unambiguously sending that message and being able to decode it. And that's when Huffman encoding comes in. So let's go back to pineapple banana. If we're using Huffman encoding, we need to go through 3 steps. The first is to create a priority queue. And what that does is it looks at how many times we've used those letters. That's called the frequency. We then use a binary tree to show how frequently used our letters are. And then finally, we have to traverse the binary tree. Traversal is just following one of the branches all the way down from the root, which is at the very top, all the way down to our leaf nodes. So initially, we order them in the least frequent down to the most frequent letter. And what we can then do is we can start creating our binary tree from the bottom up to the top. So first of all, let's use I and L. Now, I and L are then combined to IL, which has a frequency of 2, because I was only used once, L was only used once, and if we combine them together, that would be used twice. We can do exactly the same for space and B, because there's only 1 space, only 1 B. And then what we can do is we then change our priority queue. So we've taken out IL, space, and B, and we've combined them into their new 2 nodes. And we put them back in the correct place in our priority queue. So they're still at the top because there's still a frequency of 2. Next, what we do is we take the next single letter and we add that to our binary tree. So we just keep combining. E has a frequency of 2, so it can be combined with space and B. It could technically be combined with I and L as well. We then have a frequency of 4. We can then update our priority queue. And Next, we're going to pop P in because that's the next least frequent single letter. That's combined with I and L because that's now the least frequent node in our tree. That creates PIL with a frequency of 5. And again, we're going to update our priority queue. We're going to pop N in there. N has a frequency of 3, which creates NE space B with a frequency of 7. A is next. And then we can move on. Now this is an interesting bit. We've now built our tree all the way up to the top. And if we look at our queue, we've got no more single letters to add. So what happens now is we create our final root node at the very top by combining everything. And if we look there, our final node has a frequency which is exactly the same as the number of characters in our original message. Okay, so the reason we use Huffman encoding, it all looks very pretty, but actually there's a very important reason for it. If we look at our binary tree again, what we can do is we can add our ones and zeros, which we saw in the original bit pattern. Zeros on the left, ones on the right, and as we follow down to find a single letter at the bottom of the binary tree, we can then look at a bit pattern. And this creates our unambiguous bit patterns that we were talking about before. So if we look at P, you can see there we've gone from 0, we've gone to 1, and we've gone to 0. So our bit pattern for P is 0, 1, 0. But there's no other number that starts with 0, 1 and ends in something else. So we can't have just 0, 1. It doesn't give us another letter. It has to then follow on. So we can see there 0, 1, 0 is P, but that only has a length of 3 bits. If we then carry on and we look at some of the others, you can see I has a length of 4, N was only 2, A is only 2, but we can have these different bit patterns because they are completely unambiguous. So we can actually show this in the shortest amount of bits possible. So we can see here, if we were using our old system of just reducing down to a single reduced character set, we could have 8 times 4 bits, which is 32 bits. But actually using Huffman encoding with our pineapple banana, we end up with just 26 bits across the whole of the message. Okay, and that was Huffman encoding.